We now come to section 4, violations of regression assumptions. The point is that you run a regression. The regression makes several assumptions. It turns out that often one of these scenarios happens. If you recall, one of the assumptions is homoscedasticity, which means that the variance stays the same. If homoscedasticity is violated, then you have a situation called heteroscedasticity. So we are going to study that. For heteroscedasticity, which is a violation, we need to understand what is it, and very briefly I've described what it is, and we'll go into a little more detail. If this happens, if we have heteroscedasticity, which is a bad thing, what is the impact on our statistical inference? How do we detect heteroscedasticity and how do we correct it? Another possible violation is serial correlation, where the error terms are correlated. The third possible violation that we'll discuss is multicollinearity, where the independent variables have some relationship with each other. Those are the three major ones. And then section 4, all these are actually subsections in part 4. The fourth subsection is simply a summary of the issues associated with these violations. All right, let's start with heteroscedasticity. This situation, heteroscedasticity, refers to a scenario where the error term varies across observations. If you have this situation, x variable and the y variable, this is your dependent variable, the variation or the variance is relatively small over here, but as x increases, the variance of the error terms is increasing. You can just see that visually. So this is called heteroscedasticity. Within heteroscedasticity, there are two subcategories: unconditional heteroscedasticity and conditional. Unconditional heteroscedasticity means that this variance, the variance of the error term changes, but that is not a function of x. In other words, you have a situation like this, that sometimes the variance is low, sometimes the variance is high, then it is low, then it might be low for a while, then it might be high. So the variance changes, but there is no relationship between the change in variance and the independent variable. So this is unconditional. This actually is not a problem. The problem is when we have conditional heteroscedasticity. There the variance of the error term depends on x. If you just look at the scatter plot over here, does this look like unconditional or conditional heteroscedasticity? Conditional. This looks like conditional because as x increases, then the variance of the error term is increasing. Right? So in general, if we say we have a heteroscedasticity problem, we are saying that we mean that we have a conditional heteroscedasticity problem. When you have heteroscedasticity, what are the consequences? So consequences of heteroscedasticity, the f-test for the overall significance of the regression is unreliable. So you will do an f-test that's not reliable. The other is that coefficient estimates are fine, but standard error is understated. What does this mean? When you run the regression, you will get a coefficient. You will get B1 is equal to something, B2 is equal to something. Let's say B1 is 0.7, B2 is, let's say, 2.3. I'm just picking numbers. If you have conditional heteroscedasticity, these numbers will be okay. But the standard error that you will get in your regression output, that is going to be understated. If the standard error is understated, what happens to the t-stat? What is the t-stat? The t-stat is your estimate minus the hypothesis, so that's not impacted. But the standard error is understated. If the standard error is understated, then your t-stat is overstated. What's the problem with an overstated t-stat? The problem with an overstated t-stat is that you will reject the null hypothesis. So you will be happy. You're generally happy when you reject the null hypothesis. So you will incorrectly reject the null hypothesis because of this, or there is a risk of that happening. Okay, this is the consequence of heteroscedasticity, and specifically conditional heteroscedasticity. How do we test for this? You do the Bruch-Pagan test, and here we set up a null hypothesis that there is no heteroscedasticity. If you reject the null hypothesis, then you actually have heteroscedasticity. Now, what I'll do in the interest of time is, in this particular lecture, I'll not go into the details of the Bruch-Pagan test. And there are two reasons for this. One reason is that the learning objectives do not explicitly say that you need to know this. And second, in the interest of not inundating you with information right now, I'm just telling you that this is the Bruch-Pagan test. There is a good chance that if you get this on the exam, you need to know that this is what you do to figure out whether there is heteroscedasticity or not. And this Bruch-Pagan test has to do with studying the residuals. But I'm going to make available an appendix set of videos to this reading. So those who have the time and interest and want to be very diligent, you can then listen to those videos, and then the Bruch-Pagan test is explained in a lot of detail over there. The advantage here also is that, if you don't have too much time, at least know this. And then if you have time, then there is more for you to do. Okay, how do you correct for heteroscedasticity? You can do the following. You can do something called robust standard errors. This corrects the standard error of the linear regression model. So this corrects the standard errors associated with the coefficients to account for conditional heteroscedasticity. What is it saying? Actually, in your regression software, you will have a little checkbox that says correct for conditional heteroscedasticity. When you check that checkbox, what will it do? It is going to take the standard error and bump it up by an appropriate number. How it happens, you don't need to know. You just need to know that that's how it works. So if the standard error is bumped up, then the t-stat comes down. And if you can reject the null even with that lowered t-stat, then you're okay. Generalized least squares is another method. This modifies the original equation in an attempt to eliminate heteroscedasticity. But the recommended and more popular method is robust standard error. If you have some time, you can read examples 7 and 8. Example 8 is the detailed one, and I will actually have this in the appendix video. Example 7 is a very quick and simple read. All that happens in example 7 is that these researchers are doing a test, and depending on whether they correct for heteroscedasticity or not, they get a different result. Just emphasizing the importance of doing this. Okay, next, serial correlation. What is it? This is where errors are correlated across observations. And if you take a situation like this, if you have a regression line which looks like this, and you have actual data that looks like this. So these are the error terms. Are the error terms correlated? If you have a positive error term, can you predict that the next error term will be positive? In this, if you have this sort of a situation, which often happens in time series data, for example, then there is a serial correlation problem. What you really want is a situation where you cannot predict the next error term. If you can predict the error term, that means there is a violation in the regression assumption. In this particular reading, we assume that when we have independent variables, these independent variables are not a lagged value of the dependent variable. This will happen in the next reading, which is time series, where we have lagged values, but in this reading we assume that we don't have lagged values. So what are the consequences of serial correlation? And this should be easy to remember because it is the same as heteroscedasticity, roughly speaking. The coefficient estimates are fine again, but the standard error is understated. The t-stat and the f-stat will be overstated, so you will happily and possibly incorrectly reject the null hypothesis. So incorrectly reject the null hypothesis, and if you remember one of your favorite aspects of level 1, that is the type 1 error. Okay, next, how do you test for this? You test using the Durbin-Watson statistic. Now here again, I'll have this in the appendix because the learning objectives don't explicitly make a big deal of this. They don't even mention the Durbin-Watson statistic. So it is in the curriculum, it is mentioned in the examples. So I have it in my appendix video. How do you correct for serial correlation? You use what is called the Hansen method, where you adjust the coefficient standard errors. What does this mean? There is a standard error associated with each of the coefficients. So those are adjusted, and this is actually the recommended method. The other is to modify the regression equation itself to eliminate serial correlation. Alright, next, multicollinearity. This is where two or more independent variables or combinations of independent variables are highly but not perfectly correlated with each other. What are the consequences? This actually causes the standard errors to be inflated, which is different from our previous two scenarios. If standard errors are inflated, what happens to the t-stat? So t-stat is going to be lower. If the t-stat is lower, then what happens? You do not reject the null hypothesis, where maybe you should be. Okay, so that's the consequence of multicollinearity. How do you detect? These are words of the curriculum, that multicollinearity exists. So it really is a matter of degree. So it is to what extent does it exist? Because when you are running regression, if you think about your basic economics and finance, variables tend to have some relationship with each other. If you think about things like interest rates, exchange rates, and inflation and so on, all of them are in some way interrelated. So when you are running regression, it is more a question of what is the degree of the relationship. If the degree of relationship is low, then you're okay. If it is high, then you are not okay. What are the symptoms? If you have a high R squared and a very significant F stat, but you have inflated standard errors and low T stats for coefficients, right? So high F stat, but the regression coefficients have a low T stat, that is one of the symptoms, and you need to go deeper. Fortunately for us, the curriculum explicitly mentions that you don't need to go too deep into this. Just know the basics. One of the corrections is to omit one or more of the X variables. So if the X variables are related to each other, then it is only logical that you remove one or more of those variables. You can take a look at example 9 in the curriculum, which deals with this topic. So on this slide, we are simply taking a table from the curriculum where we summarize the most important points, and I would highlight this as very testable because it is taking out most of what we've talked about over the last few minutes. So heteroscedasticity, what is the effect? F-test is unreliable, standard error will be underestimated, so t-stat will be inflated. Solution is to use robust standard errors. What does this do? This will actually bump up the standard error, which will deflate the t-stat. Serial correlation, similar issues. The t-stat and the f-stat are too high. Are the coefficients okay in these two? Also in multicollinearity, the coefficient estimates are fine. It's only the t-stat and the standard error which is problematic. Okay, so just remember everything that you see on this table. When you are doing a revision towards the end, focus on this one. Okay, now we come to model specifications and errors in specification. What is the point over here? One of the most important things to do when you are running a regression is to specify the model. So you need to know how to specify a model, what are the principles. So that's covered in section 5.1. And then these other sections are brief sections which deal with the typical issues that you might face when specifying. So what are the different types of misspecified functional forms, time series misspecifications, and so on. All right, let's talk about the principles of model specification. The first one is that the model should be grounded in cogent economic reasoning. This avoids the spurious correlation issue. This is the opposite of coming up with results through data mining. So here when you have an explanation such as saying that the bid-ask spread percentage is low based on more market makers or based on higher market cap stocks, there is a logic to that. There is a financial or an economic logic. So the model should have cogent economic reasoning. If it doesn't have any reasoning, then you might connect this with something you studied at level 1 where you talked about a data mining bias or data mining issues. How do you identify potential data mining issues? By saying that this relationship doesn't have any logical explanation. All right. Next, the functional form chosen for the variables should be appropriate given the nature of the variables. Again, going back to example 1, given the nature of the variables, the functional form included a transformation. Imagine if we did not do that transformation and we just talked about the bid-ask spread percentage and X was the number of market makers and X2 was the market cap. Would the model make any sense? You would have 5 market makers and 100 million as your X2. You would get very strange numbers. So you need to use the appropriate functional form. If you have a relationship that is a y is equal to x squared sort of relationship, then your transformation needs to include a square. So this is more an art where people who are familiar with the economics of the underlying situation typically are the ones who specify the models. All right. The model should be parsimonious. Fancy word, all this means is brief. You don't want more variables than necessary. If you can get a perfectly decent adjusted R squared, you can get a well specified model with few independent variables. That is better than adding many more variables. And adjusted R squared helps with that. The model should be examined for violations of regression assumptions. So you run a regression, you need to make sure that the 3 major assumptions or violations, they are not happening. In fact, you need to verify that all the assumptions hold true. And finally, the model should be tested on outer sample data. So you define a given model using a certain sample of stocks that you took out from NASDAQ, right? So if we go back to example 1, you created this model and you picked up 1800 stocks. And the model works great in predicting the bid-ask spread for stocks that are part of that data. But then you go to, let's say you draw another sample from US-based stocks. Does your model also do a reasonable job of predicting the bid-ask spread in that other data set? If it does, then the model has value. Otherwise, the model is only predicting that little bit of data that you have, right, which is not immensely valuable. Okay, so these are the basic principles of model specification. You need to remember them. Section 5.2 deals with the different types of misspecified functional forms. Whenever we estimate a regression, we must assume that the regression has the correct functional form, but this assumption can fail in several ways. So how can it fail? There are 3 major ways that we look at. One or more important variables could be omitted from regression. All right, so again, going back to example 1, which is our anchor example for this reading. We said that the bid-ask spread, which was our dependent variable, depended on the number of market makers and the market cap. Is it possible that somebody who doesn't fully understand this market just says that this Y, or the bid-ask spread percent, only depends on the number of market makers, and he runs a regression? What has he done? Is the model misspecified? It is misspecified because it has omitted an important variable. So take a wild guess what results. You have what is called an omitted variable bias, very appropriately named. And then when you do this, you will get a regression coefficient, but those regression coefficients are inconsistent. You will keep hearing the words biased and inconsistent. Those are fancy ways of saying that those variables are wrong, right? So example 10 actually does this. It omits one of the variables and then shows you, okay, if you omit the variable, then here is the relationship. And oh, by the way, that relationship is inconsistent now. The coefficients are inconsistent. Okay, then the second scenario. One or more of the regression variables may need to be transformed. For example, taking the natural log before estimating the regression. Okay, that again is obvious. Given the nature of the data, a transformation might be necessary. Is it conceivable that somebody who isn't too fond of mathematics but wants to run a regression is scared of the E and the log and all that, so he just runs his regressions using basic data without the transformation? I can imagine that. What will then happen? So you will have another type of misspecified model where you have the right X values and the right dependent variable, but they are not properly transformed. So that also classifies as a misspecification. The third scenario is that the regression, and real quick, examples 11 and 12 can be read. Okay, so they are fairly straightforward. I think from a testability perspective, knowing the concept is actually more important than understanding all the little details. And here somebody had asked a question earlier about how can you tell whether the relationship is linear or not. And when you read example 11, and they actually create some scatter plots to show that the relationship is nonlinear. And when you see an exponential relationship, that you know that log-log type transformations need to take place. Okay, 3. The regression model pools data from different samples that should not be pooled. And the best way to understand that is to look at this. So if you pool data from two sources which are separate and different, and you plug it into your regression software, will the software give you a regression line? It will. It will give you something. But when you actually create scatter plots, maybe these two sets of data should not really be pooled because they look like different data sets. So this is another issue that can create a misspecification problem. The next category is time series misspecification. What does this mean? You probably don't remember the regression assumptions by number, but in one of the earlier slides we said that one of the regression assumptions, it was actually the third one, is that the error term has an expected value of 0. That I hope you remember. So the expected value of the error term is 0. When working with time series data, this assumption is frequently violated. Why do you think that's the case? Because most things in business and finance move in cycles. So when you have a pattern or a cycle and you build a linear regression line, then are these error terms expected value 0? No, one particular error term means if this is positive, then the next one most probably is positive. So this does happen. When this happens, then the estimated regression coefficients will be biased and inconsistent. Now, just to check your understanding here, how is this part in bold, estimated coefficients will be biased and inconsistent? How is this different from what we discussed in heteroscedasticity and multicollinearity and so on?
So the estimated error is going to bias. standard error was understated and t-state was overstated.
The difference between what we are seeing here and what we saw earlier is that here the coefficient itself is biased and inconsistent. What does biased mean? That it's either biased up or down.
Like there were error before.
So the coefficients are wrong here when the model is misspecified, whereas in the past, under the three areas that we discussed, heteroscedasticity, multicollinearity, and serial correlation, there the standard error and the t-stat was biased. Okay, so I've actually put that over here, but this is testable. Because again, you can easily see two analysts discussing a regression and confusing whether it is the t-stat which is biased or the actual coefficient which is biased. So very testable. Three common problems that can create this type of time series misspecification are given right here, including lagged dependent variables as independent variables in regression with serially correlated errors. So this is a classic issue, and how we deal with this comes in the next reading on time series. Let's look at the second one now. Including a function of a dependent variable as an independent variable, sometimes as a result of the incorrect dating of variables. So here's what's going on. If you have y is equal to b0 plus b1x, and it turns out that x is actually a function of y. So somehow x depends on y. Will there be a statistically significant relationship as far as your regression software is concerned? Obviously. But does it have any meaning? No, because x already is in some ways a function of the dependent variable. So this is another specification or misspecification issue. And finally, you can have a situation where independent variables are measured with an error. So what does that mean? That is shown in example 14. You might vaguely recall this from level 1, that you have something called a Fisher effect, which connects inflation and interest rates. Right? Now, in an earlier example, which I alluded to but did not discuss, there is a relationship between expected inflation. So expected inflation was the independent variable, and this was being used to predict T-bill rates, which is interest rates. Now, the correct relationship is between expected inflation and interest rates, because I hope you know this, that your nominal interest rates depend on expected inflation, not actual inflation. But then if you incorrectly run a regression which is using actual inflation, not expected, then you are doing the third sort of error, which is this one. You are using, one of the independent variables is measured with error, because what we are saying here is that your actual rate of inflation is expected plus this something, which effectively is the error in this context. Alright, we are getting close to the end of this. What are other types of time series misspecification? And just take this at a high level now, because this is covered in detail in the next reading, which is on time series. The most frequent source of misspecification in linear regression that use time series from two or more different variables is called non-stationarity. Okay, now what does this non-stationarity mean? This means that the mean and variance are not constant through time. That is the very high level simplistic definition. So if you have a given variable and the mean is changing over time, that's a problem. If the variance is changing, so if you have the mean stays the same, but the variance changes over time, that's also a problem. Okay, then this data is called non-stationary. Situations where this happens, because when this happens, that messes up our regression, and we need to have ways of dealing with this. This happens when you are looking at the relations among time series with trends. For example, if you are looking at the relationship between consumption and GDP, Do both of these have trends? So consumption also moves in cycles. Sometimes in a given economy, consumption is high, then low. What about GDP? That also has trends, it has cycles with time. So when you look at these two, the relation between these two, there is a chance of running into this particular problem. Also relations among time series that may be random walks. And again, random walks will be discussed in detail in the next reading, but in a random walk, the next particular value of a variable depends on the previous value. Like the next value of the stock price depends on the previous value. The next value of an exchange rate depends on the previous value. Not going into details here because you'll see a lot of this in the next reading. Okay, the last section of this reading is models with qualitative dependent variables. This is a short section in the curriculum, and I've actually taken text from the curriculum that I think best summarizes what you really need to know. The first thing you need to know is what is this qualitative dependent variable. And before reading this to you, I'll explain in very simple terms. Do you remember dummy variables? What were they? Dummy variables were independent variables which could take a value of 0, 1. Qualitative dependent variables are now on the dependent variable side. So this is where the dependent variable is 0 or 1. Let me now go through the formal definition. Qualitative dependent variables are dummy variables used as dependent variables instead of as independent variables. So this is the definition from the curriculum. Now you might wonder, where is this useful? And the curriculum gives the best example of where this is useful. For example, to predict whether or not a company will go bankrupt. So is this a binary prediction? So you want to predict either bankrupt or will not go bankrupt. So this is a classic application of a qualitative dependent variable. We need to use a qualitative dependent variable, which is bankrupt or not bankrupt, as the dependent variable, and use data on the company's financial performance, such as return on equity and so on, as independent variables. Are the independent variables dummy variables here? No, the independent variables are not dummy variables, but the dependent variable is a dummy variable. The point is that when you have a situation like this, predicting a yes or a no, bankrupt, no bankrupt, default, no default, then linear regression is not the right tool to use. Okay, so linear regression is not appropriate in these situations. So we have other tools. Fortunately for us, we don't need to go into the details of the other tools. You just need to remember their names, and you need to remember those names because they are mentioned in the learning objectives. So what are the three names to remember? Probit, logit, or discriminate analysis. So these are the three names to remember. And unfortunately, it is just memorization here. There isn't too much logic. So probit and logit models estimate the probability of a discrete outcome. What do we mean by discrete outcome? So the yes, no. Given the values of the independent variables used to explain that outcome, the probit model, which is based on the normal distribution, estimates the probability that y is equal to 1, this is the dependent variable equal to 1, given the value of the independent variable x. The logit model is identical except that it is based on the logistic distribution rather than a normal distribution. This is just another sort of distribution with a high kurtosis. That's even that high kurtosis you don't really need to know, you just need to know that it is based on a different distribution. Does every distribution have to be a normal distribution? No. So this is based not on a normal distribution, it's based on a logistic distribution. So just remember L for logit and L for logistic. And finally, we have discriminant analysis. This yields a linear function which can then be used to create an overall score. Have any of you heard of this thing called the z-score model? So in credit analysis, what you do is you evaluate a company along several parameters, and based on things like the current ratio and the debt to equity ratio and various other factors, you come up with a score, and then you say that above this score means that probability or default, or it will not default, and with this score range the chances are of defaulting. So that z-score model is an example of a discriminant analysis where you make the prediction based on a score and the score is based on several variables. That is all you really need to know for section 6. Okay, that's the end of this reading. Let's do a quick summary. As I keep saying, one of the most important aspects is the analysis of variation. When you look at your regression analysis, so the top section will be essentially the coefficients. So you will have your B0, B1, etc. And then you will have the t-stats and the standard errors. But before you go into the details of this, you will have to look at your f-stat, which is based on basically your regression data, your mean squared numbers. So high f-stat is good, and there'll be a significance, a low significance is good. What is the f-stat telling us? That basically you do the f-test to determine whether all the coefficients are 0 or not. And hopefully you want to reject that null hypothesis. If you reject, then you go on and study these coefficients. You need to know all the regression assumptions, the 6 assumptions that we talked about. All right, I mentioned f-stat, that's over here. You need to know the r squared and the adjusted r squared. You need to understand dummy variables. Here we are talking about the independent dummy variables. So 0 or 1. And if there are n states of the world, then you'll have n minus 1 dummy variables. Then we have these 3 typical violations. Heteroscedasticity, where the issue is conditional heteroscedasticity. There the variance of the error term is conditional on the independent variable. Serial correlation, this is where there is a correlation between error terms. And multicollinearity, this is where there is a substantial relationship between one or more of the x, the independent variables. Model specification issues, you need to know the various issues. First, you actually need to know what are the principles of model specification, and then you need to know the typical issues. The issues might be not doing the transformation properly, or missing out on an important x value, an important independent variable. And finally, we talked about qualitative dependent variables. This has to do with a binary number for the dependent variable. So this is mostly memorization. All right. As I keep saying, go over the summary, review the learning objectives. I've done some of the examples. The biggest one is example 1. In my appendix video, there'll be references to more examples. Doing the practice problems, as always, is essential, and try to also do practice problems from other sources. Unlike level 1, the quant at level 2 is a little more tedious, requires memorization of several terms, so please do that. And the memorization happens best when you practice questions. All right, so good luck.